All right, so ladies and gentlemen, up till now when we've been talking about the integral, we've been looking at the indefinite integral. What we're going to now take a look at is the definite integral. And the difference is, when you've been looking at your integrand, you have not seen these bounds, this lower bound or upper bound on your integral. So when you've got a function that is continuous on a closed interval a to b, then f is integrable on that particular interval. And the net signed area a between the graph of f and the interval a to b is, are you all right, Sean? All right, I can move you if you're going to be distracted. So like I said, remember, when we do our integration, we are talking about the area under the curve between your function and the x-axis. So again, the lower bound is a, your upper bound is b, and we're going to integrate f of x. All right, so you're going to be looking at these lower bounds and upper bounds now. If a is in the domain, we define, first of all, if your lower bound and upper bound are the same value. So if you're looking at a lower bound of a, upper bound of a, then the area under the curve is just going to be equal to 0. All right, so that's one theorem when you're dealing with your definite integral. If you are dealing with a function that's you can integrate on the closed interval a to b, typically you want the lower bound to be the smaller value, the upper bound to be the larger. Occasionally they will give you an integral where the lower bound is larger. What you can do is you can rewrite, putting your the lower bound on the bottom, your upper bound on the top, but you have to negate it. All right, so that's another theorem when you're dealing with your indefinite integrals. So some theorems that we learned when we talked about the indefinite integral also apply for the definite integral. For example, if you're talking about your constant rule for integration, if you have a constant multiplied by a function and it's a definite integral, you can pull out your constant, which is your c, times your indefinite integral from a to b of f of x dx. So you can integrate your definite integral and then multiply by the constant and evaluate your integral. Same thing, your addition property also applies for the definite and the indefinite integral. So we can integrate from a to b of f of x dx, add it to your definite integral from a to b of g of x dx. So like I said, these properties hold true for the definite and the indefinite integral. Same thing with your subtraction theorem. So we, again, can integrate from a to b of f of x dx minus your integral from a to b of g of x dx. So these properties, like I said, are the same. If you've got your function and you're looking at your closed interval and it contains 3 points a, b, and c, where c is some point between a and b, you can break up your definite integral into two smaller integrals. So for example, your integral from a to b of f of x dx is equal to your integral from a to c of f of x dx plus your integral from c to b of f of x dx. So what that means is when you're dealing with your lower bound and your upper bound, you can split your integral at some value between a and b and add those two together. When we get to our improper integrals later on in Chapter 7, we will be taking a look at why we need to split those. But this is another theorem for your definite integral. Okay, so we can split it and just add those two integrals together. All right, so now let's take a look at so what we're going to concentrate on today. We'll get into the fundamental theorem of calculus next week. But one way you can actually evaluate your definite integral is by sketching the graph and then using geometry formulas to calculate the area under the curve between your function and the x-axis. So for example, if I wanted to take a look at your definite integral from -5 to 7 of your function 5 dx. Well, first of all, what does the function 5 look like? So let's go ahead and graph it. What graphically does 5 look like as a function? Just a horizontal line. So I know it's a horizontal line intersecting the x-axis at 5. And again, what I want to do is I want to evaluate this definite integral from -5 to 7. So on my x-axis, I'm going to go from negative 5 to 7. So here's my function y equals 5. And I want to evaluate it from negative 5 to 7. So again, this is the area I want to calculate. I want to calculate the area under the curve from the curve to the x-axis. What geometry shape do I have here? It's a square rectangle, so we all know how to find the area of a rectangle. So if I calculate the area of this rectangle, that's going to tell me then what you've just done if you've just evaluated this definite integral. So the area then is going to be equal to, we know it's length times width. So again, the length is going to be, well, 7 plus negative 5 is going to give me 12, times the height of this rectangle is 5. So 12 times 5 is 60. So that's one way you can evaluate a definite integral. You can sketch the graph, and then you can use appropriate geometry formulas to calculate the area under the curve. Like I said, we're going to talk about the fundamental theorem of calculus, where we're not going to have to graph it next week. All right, so now let's take a look at B, sine of x, going from negative pi over 2 to pi over 2. So if I sketch my graph, sine of x from negative pi over 2 to pi over 2. Well, what is the sine of negative pi over 2? The sine of negative pi over 2 is what? Negative 1. So at negative pi over 2, think about what the graph of sine of x looks like. This would be your minimum, goes back up to 0. Then at pi over 2, what's the sine of pi over 2? The sine of pi over 2 is 1. So what I'm trying to do is calculate the area between your function and the x-axis, so that part right there, and then again the part that's above the x-axis right here. Now, mention this back when we started chapter 5. If the area is under the x-axis, so it's below the x-axis, this area is negative. So we have a negative area right here. This area here is positive. Are they symmetrical with one another? So what is that area going to be? This area is simply going to be 0. We'll talk about total area and absolute area later on. When we talk about total area and absolute area, that's where we would be looking at the absolute value, and we would negate it. All right? So any questions on those? Let's take a look at the absolute value of 3x plus 2, and I want to integrate from negative 2 to 0. So I only want to sketch the part of my absolute value function from negative 2 to 0. So if I plug negative 2 to find out the y-coordinate of this point, when I plug negative 2 in for x, well, 3 times negative 2 is negative 6. Negative 6 plus 2 is negative 4. And then when I take the absolute value, it's going to be positive 4. So I have this point negative 2, 4. At negative 1, negative 3 plus 2 is a negative 1, and when I take the absolute value, that's going to be a 1. When I plug in 0, 0 is going to be 2. Well, we know that the absolute value function looks like a V. Again, this point, remember, is down here at 1. The question is, we need to know where the vertex is. So where is the vertex of this absolute value function going to be? Where is it going to be hitting your x-axis? It's going to be hitting your x-axis at what x value? Not 0. Negative. So now, again, you've got the absolute value of 3x plus 2. We want to know the x-intercept for this, don't we? We know it's going to hit the x-axis somewhere because we don't have a vertical translation going up and down. So we know the vertex is going to have to be somewhere on the x-axis. So what am I going to set this equal to? I need to set it equal to 0. So then when I solve this, 3x plus 2 is equal to 0. X is going to be equal to negative 2/3. So I know that the vertex of this absolute value function is going to be right here at negative 2/3. So this is what the graph looks like from negative 2 to 0. Any questions on how I came up with that? So now, what kind of shapes do I have here? I have two what? Triangles. So here is triangle number 1. here is triangle number 2. So all I need to do is find the area of each of these 2 triangles, and then I'm going to add them together. So the area of my first triangle. Well, what's the formula to calculate the area of a triangle? 1/2 what? 1/2 base times height. So 1/2 base. So what's the base of my first triangle? Remember, this x value right here is -2/3. So what's the base of this triangle going to be, the larger triangle? It's going to be what? Well, it's 1 plus what? 1 1/3, which as a mixed number is going to be 4/3. Times, what's the height of this triangle? Well, when x was -2, remember, I found the height to be at what? 4. So it's going to be a height of 4. So when I calculate this, I end up with, let's see, 8/3. Okay, so any questions on how I found the area of the first triangle? Now the area of my second triangle. Still going to be 1/2 times. What's the base of that first triangle going to be? The base is going to be what? What's the length of the base of this triangle? 2/3. And then the height's going to be where it's intersecting my y-axis right here, which is at what? 2. So then the area of my second triangle is going to be what? It's going to be what? 2/3. So now to find the area from -2 to 0, I'm simply going to add 8/3 plus 2/3. So that's going to give me a 10/3. Okay. So I can add just those 2 areas together. Well, now let's take a look at D. So for D, the square root of 9 minus x squared, when I go to sketch this graph, it's not a shape I'm quite familiar with. So what I want to do, let's see if I can get rid of the square root and possibly identify what shape this is going to be. What can I do to both sides of this equation to get rid of the radical? I can do what? Square it. So I have y squared is equal to 9 minus x squared. Anybody want to take a guess what shape this is going to be? Circle. Because I can write this as x squared plus y squared is equal to 9. What's the radius of the circle? The radius is 3, and the center is where? 0, 0. But now I only want to look at this circle from 0 to 3. So there's 3. There's 3. So I'm only looking at this part of the circle. So how much of the circle's area am I going to be using? 1/4. And so to calculate the area of a quarter of the circle, it's 1/4. What's the formula to calculate the area of a circle? It's going to be what? Pi r squared. So I'm only calculating the area of a quarter of the circle. So what's the radius of the circle? The radius is what? 3. So it's going to be 9 pi over 4 for this particular area. So any questions on how you can sketch your picture and then calculate the area under the curve using your appropriate geometry formula? All right, so let's take a look at another one here. So we've got this piecewise function, the absolute value of 2x minus 1 where x is less than 0, and 1 where x is greater than or equal to 0. So again, if I look at this particular graph from -1 to 0, if I plug -1 in for x, well, -1 times 2 is -2 minus 1 is 3 when I take the absolute value. And again, at x equals 0, the y value is 1. Again, I know the absolute value is some kind of v. This is the shape I come up with. It's not a perfect triangle, is it? Because the triangles side is not going to the origin. So what you may have to do is take this region and divide it up into two different type of geometric shapes that I could calculate the area for. So for example, since this point is right up here, 1, what I can do is I can divide this region up into a triangle and then into a rectangle. And then I can calculate the area of each individual shape. So I can calculate the area of the triangle, and then I can add it to the area of the rectangle. So to find the area of the triangle, I know the formula is 1/2 times. What's the base? The base has a value of what? 1. Now be careful of the height. We're not starting at 0 with the height of this particular triangle. What's the height of this triangle going to be? 2. So the area of the triangle is just going to be 1. Now the area of the rectangle, base times height. What's the length of the base of this rectangle? The base is what? 1. The height of the rectangle is 1. So 1 times 1 is 1. So to calculate the area, going from -1 to 0, it's going to be 1 plus 1, which is going to give me a 2. So like I said, when you do your sketches, if it turns out to be a shape that you don't recognize, you may have to divide it up into different regions. All right. Is there possibly for some of the graphs 2 different ways or more than one correct way to divide it up? Absolutely. But in the end, your answer should be the same. All right. Let's take a look at B. So I'm going to go from 0 to 4. Well, when x is greater than or equal to 0, the y value is 1, which means I have another horizontal line. So again, I'm trying to calculate the area under the curve from 0 to 4. So you guys go ahead and do this one for me on your own.